Now we have two spins. It will be different couplings. There will be a spin.
But you see, I see. Okay.
And this would become coherent.
Yes.
Two spins. And usually it sounds like it will be on the same order. The count.
Okay.
Maybe there's some core elements that
that would be very good. You know, I said, right. I said, we want back to our person folks. Okay. Yes. Now. Yeah, I think it's not, yes. Yeah.
Okay, we'll start our session now. Okay, our first speaker is Paul from ETH. Paul, can you start?
Yes, thank you. Can you hear me well?
Yes, yeah, okay.
Very good. Thanks a lot, first of all, for the very kind invitation. I'm very sorry I couldn't make it in person. It's really high semester here. And also we start beam time Monday at PSI, so it was really not possible, but it was really great to follow the workshop, at least online, and shame I couldn't participate more to the discussions. Anyway, I would like to present the latest results of MuMASS, and actually the first results of the NACC4 experiment running in Muon mode. So these two experiments are using Muons beams, but with quite different energy scales. MuMASS at PSI, we use keV muons, while for the NACC4 experiment running in Muon mode at the CERN SPS, we use, call it sub-TV to sound more fancy, but actually Balint already presented before 160 GeV muons. So let me start with MuMASS. This experiment is running now. We proposed it in 2019, and we started taking data in 2020. So I'll present part of the results we have and also the future prospects. So Dimuonium was nicely introduced this morning by Sotaro Kanda. And just as a reminder, is the muon electron bound state is lifetime is limited by the lifetime of the muon to 2.2 microseconds. It was discovered, some of you might remember, by Hughes and his collaborators in the 60s by looking at muonium spin precession. As soon as you bound the muon with an electron, the electron is a large magnetic moment, you see the spin precession going much faster. And since that has been used for many tests of bound state QED, it's great because it's a system where you have no uncertainties from the nuclear side effects. And in principle, it's a very nice system to test new physics, because if you would see any deviation from the theory and the actual experiment, if both are done correctly, could be a signal of new physics. And as we have seen as well, there was a talk showing that there are prospects as well to improve on the, for example, muonium to anti-muonium conversion. Also, it was mentioned the measurements with muonium are very relevant to extract fundamental constants such as the muon mass and the muon magnetic moment. The muonium spectroscopy theory and experiments until recently, I tried to summarize them here, where most of the experiments were done in the 90s, and in the late 90s, the best determination of the hyperfine splitting of the 1s2s were done. Here I'm plotting the right side is the measured quantity, and the left side is the uncertainty for the experiment in black. And what I put here and on the left we have the uncertainty due to uncalculated bound state QED terms. But as you see, there is the uncertainty coming in both of those from our knowledge of the muon mass. So this was mentioned as well by Sotaro. If you, for example, measure precisely the 1s2s, what can give as an input to the hyperfine splitting measurement, which is also being currently remeasured now, we can then provide a clean test of QED. On the other end, we could take the muon mass, assuming the QED is correct, plug it in the 1s2s if we prove that, and extract, for example, the Rydberg constant free of finite size effects. There have been also some measurement of the line shift and the fine structure, and this line shift is actually what we improved recently in our measurement at PSI, and I will talk about this. And you see as well, theory improved over the years. There was a lot of efforts for the hyperfine splitting for the 1s2s, but also there was, as we have seen, the proton charge radius puzzle, which triggered new measurement, including the lamp shift in hydrogen. And this also then, as somehow as a consequence, the theory as well for the Muonium was improved. Now, the future prospect, again, Sotaro said this morning, the hyperfine splitting is aiming to reach an accuracy which is 10 times better. In the MuMASS experiment and also at JPark, we are both working to improve the 1s2s measurement, and also what we could do in MuMASS, since we already demonstrated we can measure the lamp shift, it would be quite straightforward to measure as well the fine structure at a good level of accuracy. And the Muonium lamp shift more in detail is here. You know, the lamp shift is the 2s1/2 to p1/2 interval, and what you have is the different hyperfine splitting states, and then the different transition. You basically have this transition that you can drive, and this is what I will show. We have done, we have measured all of those, and from those as well, either you take out the lamp shift, assuming that you know the hyperfine splitting from the ground state, you just scale it to the 2s state, or you can as well extract the 2s hyperfine splitting. What is interesting, if you look at the Muonium system, is that it's being much lighter than hydrogen. You have some of the corrections of QED, of bound state QED, which are enhanced because of this recoil, so-called recoil correction. So you have these terms which depend as the ratio of the electron to the nucleus mass, so either the proton of the muon. And so even with a more moderate accuracy, you can actually get access to some of those corrections which are not, for example, those accessible with the hydrogen system. So this was the experimental accuracy, and with our experiment that we did at PSI, we could improve basically by an order of magnitude. And what we exploited was the low energy muon beamline. This was also mentioned. There are different ways you take proton accelerator, you produce pions, it's the decay, the pions are dressed, they decay close to the surface, you can collect them and form a surface muon beam. But now this is quite energetic. So what you would like to do to form muonium is to lower the energy down to some keV, and this can be done in different ways. What we use here is either a solid argon or neon moderator as well, to just get from the surface muon beam some muons at the, let's say, level of electron volts. And then what we have to accelerate them, obviously, if not, they will decay. So the moderator is typically biased high voltage. We have an electrostatic mirror. We guide them to the region where we do the experiment, and on their way, the muons, they pass through a thin carbon foil, which we use for two purposes in our experiment. One is we can tag that the muon is really coming to our setup. This is in contrary from what is J-part, this is not a pulse source to Muon that comes stochastically, so we really can tag them one by one. And then what we can also do there with the carbon foil, we can not just tag the passage of the muon, but also for Muonium, both in the 1s and in the 2s state. The 2s state, let's say n equals 2 is roughly scaling like 1 over n to the cube. So you get around a factor 10 less in the 2s state, but still, this is quite still a reasonable fraction to do this lamp shift experiment. And the idea of the experiment is really very similar to what lamp did back in the day. So you have the 2s states, which, as you know, they are not allowed to decay to the 1s, so they are metastable. They fly through a region which is the region where we scan the microwave frequency. We can induce this transition from the 2s to the 2p with around 1 gigahertz. Now, when the atoms are driven to the 2p, they immediately decay to the ground state, emitting a Lyman alpha photon. But in this region, we have no detectors, and we don't detect this Lyman alpha photon. What we want to detect is when the Lyman alpha photon is emitted in this place here, we have some quenching grids. So we apply a static electric field, and via Stark mixing, we can again drive the remaining population that was not quenched here in this region to the 2p state. And in this case, what we do, we detect our Lyman alpha photon with this microchannel plate, which we coat with cesium iodine to be sensitive to these photons. And then what you expect is when you are on resonance here, you expect to detect the less population in the 2s states remaining in this region. And this gives you this kind of signal. You have the 2s that is detected on resonance. These are the different hyperfine transitions in the lamp shift. You see that this is basically the minimum when you have the resonance, because you already depleted most of the population here. And this is what we actually performed. We did all the free transition. I'm just showing the results here that we obtained first for the 2 higher frequency transition. This was just 48 hours of data taking, and with that, we could improve by 100 times the statistics compared to the previous measurements. And as you see, the statistics is the limiting factor at the moment, but the next systematic we should face is the 4s contribution, because when we form Muonium in our carbon foil, we also form higher excited states, and it happens that the 4s is lying somewhere down here. So we have this uncertainty on the 4s fraction, which results then in this systematic that we in our experiment. And this we can, as I will discuss this later. We are working on to get rid of this and remeasure. So what can we do with these results? These were in agreement with the calculations, our measure data. So we can not test yet bound state QED, but we could put some constraints of new physics. For example, probably you're familiar with the SME model of Kostelecky and his collaborators. This allows us to put some new constraints on some of those coefficients. And the other things we could constrain is this some kind of new muonic forces, and this was a proposal on Claudia and his collaborator on basically looking at the perturbation you would expect on your energy levels if you would have, for example, a new scalar or vector boson. And this was already shown, but I'll re-put it here. This is not the updated results, but that's when we published back then. This was our updated results. Is what McKeen and his collaborator put forward. A new boson could somehow provide a solution for the G-2 of the muon. Here, of course, the situation is quite complicated by the fact that the two measurements of alpha did not agree, but we still use this as a bound, and somehow we can see that for the lamp shift, we can probe this parameter space. For the 1s, 2s, and the lamp shift photo projection, we will be able to access even more of that. So what are the prospects of MuMASS? We think we can improve the lamp shift and also measure the fine structure by applying some improvement to our setup. One is to remove these higher excited states. This is something we will try starting from Monday. Actually, we have Monday beam time at PSI. We will use some electric fields which will quench before the region where we use the microwave field transition will quench mainly the 4S states. Of course, you lose some of the 2S states, but the 4S states are more easy to quench with electric fields. So we can, in this way, get rid of those and be left just with the 2S states we are interested in measuring. And other improvements we are planning, we're working on using, instead of a carbon foil, some much thinner graphene foil. This helps because when the muons goes through the foil, they scatter, and then we lose many of those muonium even in the 2S states, which are interesting for us, just because they come out with an angle that then is not accepted by our detector. Our detector is about 1 meter long, and we really detect when the muonium makes it to the end of the detector, the tagging from the muon going through the carbon foil, and then the Lyman alpha photon. So we have like this system with frequency incidence, and clearly if the muon scatter a lot, many of those don't reach there. But with graphene foils, we should be able to improve our flux by a factor which, depending on the thickness, we can get of the order of 10 to 20 from what we have now. And finally, what we will be, it was mentioned this as well, the new cool beamline is being developed at PSI. This, of course, would help greatly because you have higher fluxes and a much better defined beam. So we would think we could even go to lower accuracy. But finally, the upgrade of the Muon beamline at PSI, the IMP, combined with this MuCool, using not graphene but a gas target to produce muonium, could even bring us lower down to this kilohertz. Of course, these time scales are still very rough, but let's say there is very good prospect for this kind of measurement at PSI, especially due to these developments which are foreseen. For the 1S to S transition, I'm not showing too much here, but basically we developed all the laser system, and we had a first attempt, and we understood many problems on stability that we will be addressing, and this laser system will be ready next year for trying to actually do this for first time with a CW laser, where basically the systematic will kick in only at the level of the 10 kilohertz. So until there, the systematic is much more under control than using a pulse laser. And in the future, again, with HIMP and some further developments, one could dream of reaching at even higher accuracy. So let me switch now to the NH64 running in Muon. Actually, here I should correct this our logo. In this case, we do use Muons, and here what you see is basically the beginning of the beamline where we have the spectrometer, and then our experiment is located down here. So here the energy scale is much larger, and what we want to probe here are dark sectors, and this as well. For example, Matteo's talked about this, are a framework where one could introduce some new force between the standard model and the dark sector within some mediators. And these can be of different kinds, but I'll focus here on the dark photon portal. And in this framework, what is very interesting, you can actually reproduce the observed amount of dark matter that we see today. And this is in the case you assume that actually the two are in thermal equilibrium at the beginning of the universe, and then when this the universe is expanding, this freeze out in like the very similar to the WIMP miracle. And this then gives something which is a very nice target at accelerators. You see it here. It's maybe not the most up-to-date, but you see that this region is excluded in this parameter space, which is Y, which is proportional to this average annihilation cross-section that then reproduces in this way the observed amount of dark matter. And this is a target that we can address in ACC4 experiment and also other people in accelerator experiments. So it's very motivating to try to go and see this possibility. And here just a disclaimer, I adapted some of the slides that are coming from the PhD student that just defended this thesis last Monday, actually, Henry, and it was successful. So I'm very happy that he was really the first PhD student on this ACC4 running in Muon mode, and did a lot of the work that is presented here. So I would really like to acknowledge him. So the other motivation to search for dark photons again comes from Maxime. Is this was the situation back in 2008 when this was proposed as a possibility to explain the observed anomaly, to have this dark photon in the vertex, and this has been then excluded by an ACC4 and Babar in 2017. And here I'm just showing the situation now in 2023. These are the latest results of an ACC4 running in electron mode. This is the resonant annihilation channel, which we exploit as well. And in this also, with these statistics, actually around 10 to the 12, an ACC4 is starting to probe, at least for these parameters, alpha D01 and this canonical or benchmark parameters, and A prime equal 3 times the mass of the dark sector particle, start to probe the scalar and the Majorana radical. We already could exclude part of this. And the idea is then, is there another option which could still keep this explanation of the G-2 alive? And actually, one scenario, which is an interesting one, is this with the L-mu L-tau model. Here, you would have the Z prime boson associated with this broken U1 L-mu L-tau symmetry. And this also could then be linked with the dark matter. And it turns out that this model is very interesting because it could solve both problems simultaneously. And what we did in an ACC4 running in Muon mode was really as a first goal to try to address this model. So let me get to the experiment. And this started with a proposal in 2018. We then we were approved for some pilot runs in 21, 22, and we could accumulate, and I will present the results on those, 2 10 to the 8 muons on target. The setup was upgraded, and we collected 1.5 10 to the 11 muons on target in 23, but we didn't get to analyze it yet. As I said, Henry just finished his PhD, and we are not many people in especially this is a somehow spin-off on ACC4. So we will be getting back to this data now and work on those. But the idea is what Banent already has shown. You wanna have a very well-defined initial muon with 160 GeV. So you have to really be sure that the muon comes in with this momentum. Then it interacts with an active target, and there, as a final state, what you want to see is a scattered muon with an energy compatible with less than 80 GeV and plus missing energy. So you have some VITO and HCALs, and in the HCAL, for example, in the ECAL, you just detect a MIP compatible with a muon, but no other activity. And the experimental signature would be this muon detected with this momentum and no other energy. Normally, for the standard models event, you lie on this diagonal where the energy that you gets in is the energy that you measure. So the experiment is located in the north area, and it's located here in the M2 beamline. So it's a different location than the NA64E. We have the initial spectrometer, which is 82 meters, and we have the 16 meters here for the experiment. We are upstream of what used to be the complex experiment, now is amber experiment. So this is an area that was is in a tunnel, is not really an experimental area, but we could still fit in our setup in this shore space. So this is how the muons are produced. You have a proton on a target, you have then the hadron, the decay section, and here some beryllium to absorb hadrons, and then all the beamline driving to this band 6, where we have our first spectrometer. This is 82 meters long, and there's some quadrupoles, so the tracking here is very challenging. This spectrometer was somehow fixed in space. We couldn't really work with that. We just introduced our trackers, but one of the upgrade actually is to introduce that we did in 23 another spectrometer upstream here. But at that time, we just had this spectrometer upstream, and then the spectrometer downstream to measure the final state. And here, just some picture of the upstream and downstream part. So what we did with the simulation, we could optimize, let's say, the trigger. We actually, our trigger is this coincidence of this scintillator S0, S1 in anti-coincidence with the veto, and then to remove the halo, and then S4 and S mu, what we call, basically to really trigger only on the scatter muons. We cannot keep up with all the beam that, even though deflected, is slightly deflected. So and the beam is not pencil-like. So you really need some distance, and this distance has to optimize. And what we did is to look all this was implemented in Gian4, and also the angular differential cross section with for the angular dependence and for the fractional energy of the muon. And what you have is that at high, let's say with low masses, as you see, you have our acceptance is here. We have a low acceptance, but you have a high yield because of the cross section dependence. And so you kind of optimize this, because at the other hand, at high masses, you have a higher acceptance, but you have a lower yield. And so this is all the work we did before installation of the experiment. And then here are already the data. Here we select the incoming muon momentum in the range 180 GeV, reconstruct the track in a downstream setup with momentum less than 80 GeV, and we ask, as I said, we have some veto hadronic calorimeters, in this case after the ecal. Now we placed also one before the ecal. We have the veto, and then we require energy compatible with AMIP in ecal and HCal, and that's what you see. This is not with the full apply cuts, but you see different regions, and these regions then is what we use for extrapolation in the blinded region to estimate the background. And as you see, the main contribution to the background is the momentum misreconstruction. So you can have 160 GeV muon after the ecal that we misreconstruct as some lower momentum. And this then after is really the main contribution. After this, what we have is some hadrons decaying flights. You can have either pions or kaons, which are in the contamination of the muon beam, which can decay in a muon, and a neutrino missing energy, and the muon you still detect with lower momentum. And this is something which was also because we had this long spectrometer, and then the setup downstream in 2023, also putting another spectrometer right before the ecal reduces this greatly, as well as this momentum misreconstruction. Then we also estimated the systematic mainly related to the signal yield, so the Monte Carlo accuracy, the underlying Z-prime physics, and the trigger alignment. And here was before then after applying all the selection cut, that's what remains before unblinding. And then we got the blessing from the collaboration, so we unblinded, and actually we didn't see any events, unfortunately, or maybe fortunately for Henry, would have been quite tough to defend this thesis just before unblinding this and finding some events there, but we definitely didn't find anything as we were expecting in terms of background. So what we can then do is put some constraint on this model. Is like it's basically the parameter space. Yes, I have 0 minutes left, so I see I am basically finished. Sorry. This is our results. So we could cover here a portion which was not probed on this G-2 explanation. We can also convert it with for the dark matter here. You pick the coupling so that you can explain both in this region G-2 and dark matter. This then brings me to the future prospect. What we plan is to still run until LS3, so until 2026, and accumulate as much statistic as we can. The 10 to the 12 might be ambitious because we have high competition for the beamline. And after LS3, we plan some upgrades to really run with higher intensity. And with this, I'm sorry that I was running out of time, but I thank you for your attention, and thank you on the MuMASS team and the NACC4 teams.
Thanks.
Thank you. Sorry.
Questions?
Hi, Paolo, Mateus here. Thanks again for the talk.
Hey, Mateus.
I guess I have to ask for the Muon mode. I guess you could imagine these models that we looked for, the semi-visible dark matter models, plastic dark matter, coupled to Muons exclusively. I wonder if that's something you thought about is feasible.
To look for some kind of displaced vertex signatures.
Right. 2 Muons.
Yes. For the moment, we did not, but in principle, this is something one could study. And as you know, our setup it's quite flexible. We have the luck that one can always rearrange it, change the distances, and in principle, we could identify Dimuons. And now what we do, we simply reject them in our analysis. We ask for a single MIP, but we can clearly see in the HCAL Dimuons, and also then in the trackers, you would see them, and you could try to reconstruct the invariant mass. But yeah, this is something we did not yet study. It would be interesting if you have some ideas of some interesting models. Also, then one should check where is the decay vertex, and if you can fit it in the acceptance of the detectors. Yeah.
Thanks. The other question might be a little bit crazier. We were discussing neutrino backgrounds. So neutrinos producing some, in this case, lower energy muons. I guess you don't have any muons, but you're relatively high energy beam. Do you know at what point that starts becoming a background for you?
You mean from decaying muons and then just the neutrino flux that they create?
Exactly. Yeah, and then interactions in the target.
Yeah, I mean, our advantage here is that we really tag every single incoming muon, so it should be already like some sort of pile-up event, I think, because in some way you should we really tag them one by one, right?
Yes.
So I think this helps suppressing our fluxes are not. I mean, one can calculate the probability, but excuse me.
I guess if you tag the muons, this is never really a problem.
I wouldn't think so. Yes.
Okay, thanks. Thought I would just ask.
No, thanks a lot for the question.
Paolo, thank you for the talk and for taking your evening with us.
Thank you to you. And yes,
Right.
It was okay because it was combining a lot of stuff, and I'm not sure was was too
One
much. Maybe, yeah.
if you have any sensitivity to lepton flavor violation by fusing mu plus and E minus in the target into something invisible.
By fusing,
The target has a lots of electrons, right? And you're shooting mu
yes,
plus, right? So
yes,
if
mu minus we are shooting.
you're shooting mu minus.
Yes, we could
Well,
shoot mu plus if there is some
yeah,
interest,
if you
but
shoot
the
mu plus,
hadron background is slightly larger.
you could get to the lepton flavor violation into, I don't know, missing particles.
Mm-hmm. Yes, I mean, we didn't think of the only lepton flavor violation ideas came from Sergey Valint and from you, but this I don't yet get it. So, what would be the process?
Let's say there is a mu E current that is coupled to, I don't know, chi bar chi current, right? So you annihilate the incoming mu plus with the E minus, right?
Ah, interesting. Yes. Okay.
Just
Yes. But
just
in this case, we should really use mu plus for the
correct.
annihilation channel to work. Yeah. In principle, it's possible. As I say, we run in negative muons because the hadronic background the hadronic contamination is smaller, but it doesn't. I mean, if you think it's an interesting idea, if you have some estimates of if this is not completely excluded, we could think about, of course. Yeah.
Okay, let's thank Paul again.
Thank you. Thanks a lot. Sorry for taking more time.
Our second speaker is David.
Yeah. Do it over here. Nice. Oh, yeah. Thanks.
Okay, David, please start.
Yeah, thanks. Can you guys hear me? Yeah. Okay. So yeah, thanks a lot. It's been a very fun workshop, and I'm glad I got the opportunity to come. Thanks for having me. And also thank you for allowing me to talk about something a little bit weird. So this is some work. I'm using that term loosely. So thank you, but that I've been doing with Patrick Draper, an old friend of mine, after we were at a wedding this past. So that's
Dave, is your microphone on?
It's hooked up to me.
Is the light on?
All right. You should have told me when I asked.
Couldn't have
Okay.
a question.
All right, so I'm going to start with a story. Okay, that's a different story. All right, so you're a little kid. You go to school, you do well, you try hard, you study. You get into grad school. You think, okay, I'm gonna uncover some really amazing mysteries about the universe. I'm going to understand the universe, nature at a very fundamental level. Discover all kinds of things. You write a paper. You meet very smart people. You write a paper. All right. Set some constraints. You write a paper. Set constraints. Okay. Write a paper. You rule something out. You keep doing this, right? and you get older, and then at some point you start to wonder, like, okay, what am I doing with my life? You get a little bit depressed, okay?
Experimenters never think that.
No, of course. Well, maybe, yeah, maybe, all right, so at the cost of 6 of these, you write half a paper. Yeah, anyway, so yeah, okay, so you get a little depressed. All right, you look out the window at the world. Then you get depressed for a different reason. It's not good. Okay, this is great. And then you ask, okay, well, at least actually, no, I'm probably making things worse. This is too bad. So then you start, wondering if you can do something that's at least useful. This is we're like super violating the Hippocratic Oath of physics, right? So we're actually doing harm. So let's try. Imagine, can we at least maybe help out a little bit? So that's where I'm coming from. That's the background here. All right, now here's a bunch of caveats. I've given some other caveats already, but here are the ones I wrote down. Okay, so this isn't my area of expertise, so I'm a neophyte here, and I don't know that I have any good ideas. I also haven't had too many of them yet. This is work in progress. I don't know. So I was hoping to do my homework, and writing this talk was sort of the beginnings of doing my homework. And I'm maybe kind of outsourcing, crowdsourcing the homework that I was supposed to do. And the reason that another more practical reason that I'm giving this talk is that in recent years, I mean, I've done a lot of stuff involving new physics, mostly because of muons, but not with muons. So it's a little hard to figure out something to talk about. Okay, so the area of science that I'm going to be talking about is a little bit murky, and maybe it can be sometimes a little hard to figure out, what's actual good science and what's kind of less good science, I guess. However, it does at least touch on one of the most pressing issues that we face as a species living on this planet. So and that has to do with how do we cleanly, efficiently, safely generate energy so that we can all live lives that are convenient, and we have computers and stuff. It's fun. Okay, so bunch of apologies. So I'm done apologizing. Okay, so there's a internet personality, a YouTube personality called Limmy, and he has a nice meme. I think it's or there's a phrase of his that became a meme, and I think it's like some pretty decent advice. And that's when people give you they complain, you've made a mistake or something, you don't back down, you double down. Okay, he's just don't give up. You're not wrong, they're wrong. So all right, you guys are stuck listening to me at least, but so and I think actually maybe like the success of our last or your last president shows the effectiveness of this strategy. Even if you are wrong, just okay. Anyway, so I'm done apologizing. All right, let's talk about some stuff that I've been thinking about. All right, so this talk has to do with fusion. So that's maybe one way of extracting energy from nuclei, and so one way of thinking about that is to stare at a table which lists all of the a bunch of nuclei and their binding energy, and so per nucleon inside of that nucleus, and basically being higher up here means that you're more stable. So if you can do something that takes you up this chart, then you can extract that binding energy. You get into a much more stable configuration. You can use that energy. Maybe you can do something nice with it. And so we do that, on the high end of the nuclear chart by fission, so breaking these things up. Then you can extract energy. People do this at power plants. The bad thing is that you tend to make stuff that also wants to undergo fission or decay and then turn into bad stuff and harm people and things. So and also that's you have to go and find these very rare things and stuff, and it can be a bit of a pain. It would be nice, you know, we use a lot of things down here, make things out of stuff that lives down here, like with hydrogen, for instance. And it'd be nice if we could climb up this chart. So it would be fusion, and we could extract the energy that way from the nucleus. And there's, you know, nuclear physics is just weird. I don't know why the chart kind of looks like this, but that's what it is. It's a strange thing. So here I list a couple of potential fusion reactions that we could use to extract energy. And so they involve heavy versions of hydrogen, so deuterium and tritium, or deuterons and tritons. And you can fuse these things together. It's allowed. And then you release some amount of energy. So, you know, this is the Q value involved in each of these reactions. And so, you know, this tends to be kind of in the MeV ballpark, which is sort of the scale that you would expect if you're doing nuclear physics. Okay. And this is a lot of energy compared to if you're just doing, you know, chemistry, breaking up fossil fuels. And that's why it's nice. And also, you know, the right-hand side of this, you make some stuff that's not great, but at least it doesn't live for very long. Okay, so at least, you know, in 20 years, it's pretty much all gone. Okay, in particular, I just want to call your attention to this last one. So this is taking a deuteron and a triton, turning them into an alpha particle and a neutron. And an alpha particle is extremely deeply bound. It's very stable because of weird nuclear physics. Because of that, then you can release quite a lot of energy. Okay, so something like almost 18 MeV. And then there's another weird miracle of nuclear physics, which is that there's a resonance. So these, you know, you can imagine these guys come together and then they live for a little short period of time as a helium-5 nucleus. And it turns out that one of those helium-5s is kind of has a mass that's not so far from this threshold here. And that means that the rate for this process is something like 1,000 times larger than it would naively be if you were just, you know, doing order of magnitude guesstimates. Okay, so can we use this? That'd be cool. Well, all right. If we don't want to collide these beams, right? So, or sorry, other way around. Gave away the joke. Okay, so if we don't want to collide these, what's another way we can take, you know, these two heavy analogs of hydrogen, put them close together so that they can undergo this fusion process? So one way we could do that is by making an analog of the H2 molecule. So here's a cartoon of that, and it involves heavy versions of hydrogen nuclei, so a deuteron and a triton. They're sitting nearby. They're sitting in fact, you know, they're bound by some electron, which is orbiting both of them. And the characteristic size of this electron cloud that holds these things together is something like the Bohr radius of the electron. So it's like 1 over the electron mass, and there's a fine structure constant in there. So that's the size. And then if we want to take that data on the annihilation cross-section and turn it into a rate in this bound state, then we simply just take that cross-section and then we ask how often the deuteron and the triton sit on top of one another. So this is the nuclear wave function at 0 separation. We take that thing, we square it, and then we have a rate. So then, you know, the cross-section is pretty big, and okay, how often do these guys sit on top of one another? And the answer is not very often, and the reason is the large Coulomb barrier. So these guys are both positively charged and repel one another. And so here I'm just showing the potential as a function of the internuclear separation here. And so the point is, if you dial this down, the potential goes way up because of the Coulomb force. It comes down, and then there's some you know, region where these guys like to sit nearby one another because of the electron that they're sharing. So, you know, to calculate, if we, you know, think about the wave function here, and then we ask, okay, well, what's the overlap? How big is this thing towards the origin? We can do, you know, undergraduate WKB expansion, and it's basically related to integrating this, the difference between the potential energy and the energy from the classical turning point down to where you want to be. So just do that integral, okay? And so the point is basically the wave function here is exponentially suppressed at the origin. So this is a tough thing. This is too bad. And that exponential suppression is sort of related to the scale of the problem here. So it knows about the Bohr radius. Okay, that's too bad. Or I mean, that makes this process maybe not so favorable. But let's imagine there was a heavy version of the electron. And if we had such a yeah.
So is the point you want to make that this molecule prefers to dissociate rather than fuse, or it just like falls apart?
Yeah, basically. Or yeah, it does something else, it bumps into something else and rearranges. Yeah, so the point is that maybe the in the normal molecular state, it doesn't want to, they don't sit on top of each other very often. But if we could do something like arranging for there to be a heavy version of the electron, call it a muon. In that case, everything goes through the same way, except the characteristic scale of this thing is just down by a factor of 200. Okay, because again, the scale is the something like the Bohr radius, which is inversely proportional to this light state that binds them together. And so that changes the problem in the sense that this plot I've made here, the scale. All right, so it's the same plot. I'm just using different units. So I have the muonic Bohr radius instead of the electronic one. And then when I go to do my WKB integral, then the scale here, the length scale that I have to integrate up to, this classical turning point, is down by that same factor of 200. It's inside of, or it's in an exponent. So then the rate is enhanced by, it's exponentially larger in a muonic atom than it is, or muonic molecule than it is in a electronic one. Okay.
Wait,
Yeah.
so, I mean, if this is supposed to be like a hydrogen molecule,
Yeah.
then there's really two leptons.
Oh, I mean, okay, so it's a hydrogen ion or a molecular ion.
Okay, you really just want one.
I mean, okay, so in this picture, okay, then there's electron maybe out here or something.
Well, it's stable.
Yeah.
H2 plus is stable.
Oh, okay.
Yeah, most hydrogen we encounter is.
Like it can form this covalent bond with just one electron.
Yeah, 10 minutes. Okay, very good. Okay, so all right. This is great. Maybe we should use these molecules.
It was used by Paolo to show that the Bohr quantization rule is incorrect because it predicts that unstable H2 plus, and it was already known in the early 1920s that it's stable.
Interesting. Okay, so that's a good segue here. This is a bit of history as well. Okay, so people understood this, and in fact, the fusion that was driven by forming these muonic molecules was observed in Berkeley about 75 years ago. It's kind of amazing, and you can go and look at the paper. Here's a inscrutable bubble chamber photo, but it shows basically this process where they fire a negative muon into a bunch of hydrogen and deuterium, form a molecule, and then fusion process takes place, and the muon's ejected, and then it later decays. Okay, so then in a interesting bit of ambulance chasing, a couple months later, there's papers written in the West, also in the East, and then interestingly, it was actually even predicted 10 years beforehand. There was a person who wrote a paper in Nature. So there's a theorem that maybe if your paper's in Nature, it might not be true. So maybe this is a counterexample, but there's enough weasel words in the title here that it's you might not be able to pin it down as being false. But anyway, so this person was thinking about using this as an energy source Interestingly, they didn't even, they hadn't settled on mu as the letter for this particle. Okay, so all right, great. Now people were apparently very excited by this. Alvarez, the person leading the experiment at Berkeley, later won a Nobel Prize for something else, I think. But anyway, so he, was saying, oh, this is a super exciting thing. They'd solved all the world's energy problems even back then. The New York Times coined apparently the term cold fusion. Kind of interesting. People, wrote down prototype reactors that could make use of this fusion process, and things were kind of interesting. But when you sit down and actually do the budgeting, it's a little less rosy. So here I just have some, not so complicated equation that just parameterizes, whether this is useful or not. So what I'm computing here is just the ratio of how much energy I get out as a function of how much energy I put in. Okay, so if this is a useful way of making energy, this number better be larger than 1. Right, this is pretty obvious. Okay, so there's a few factors that go into this. We can kind of, do some back of the envelope estimates. Okay, so the energy that I put in, I have to make these muons, and I do that by making a beam of maybe protons. They carry, some energy per particle. There's some energy that's associated with them. That's this EB. Then I have some efficiency in turning, plugging the accelerator into the wall, turning that energy into the energy of the particle. So there's some efficiency, a number less than 1. So I have to put in more than 1 GeV if I want to get 1 GeV protons out of it. Then there's per particle, there's some number of muons that I make. That's this F mu. Then there is the energy released in a fusion event. That's this E fuse. And remember, in the DT fusion, this is something like 17 MeV. And then the magic of catalyzation is that I have a muon. It forms a molecule. There's a fusion event. When the muon goes, finds another deuterium or triton to bind to, and then does the same thing again. It does this many times. That's n cat, so the number of fusions that a single muon will catalyze. All right, now I just plug in some optimistic numbers. So, if I have a beam of, say, 3 GeV energy, let's say I'm very good at making my beam and I can get, extract the energy that I buy from the power company at 40%. That's pretty high, I guess. Half of these particles on average make a muon. Then for this to break even, I need to do this 1,000 times, or sorry, so each muon has to catalyze 1,000 of these reactions. Okay, so this is all right. This is a big number. It turns out that experiments have seen order 100. So it's a little bit far away from maybe 1,000, but it's not so far away that it's absolutely totally bonkers to think about. Although maybe it is a bit bonkers, but anyway. So what goes into figuring out this number of reactions a single muon can catalyze? Okay, so there's essentially the amount of time that it takes between fusion events. So once the molecule is formed, then the fusion happens relatively quickly. The rate limiting step is actually the formation of this molecule. So the muon goes and finds a deuteron, binds to it, and then it has to walk around in whatever this mixture is until it finds a triton and sticks to it. So that's actually the rate limiting step. It's not the nuclear physics. The muon better do this before it decays. So that sets a limit. And so it's essentially the ratio of the time that it takes to form these molecules to the muon's intrinsic lifetime. Then I didn't mention, but there's a whole bunch of stuff in the literature. This will come up in a second, which is another way for the muons to exit this catalyzation chain and stop being useful. And that's if this fusion occurs, and then the muon decides to stick to the alpha particle and then fly off in that way. So this is called sticking. There's a probability that this happens, and then you have to multiply, account for the, account for that when you compute how many of these catalyzations take place.
Is this a correct equation? Suppose you have 1% chance of sticking.
Yes.
And that is 99 cases I continue. And,
Yes.
In 1% case, on average, I will have 99 catalyzed cycles, right?
Yeah.
Per muon. And
Yes.
that is, according to your formula, if this tau fuse is very small, you can still go above it.
Sorry, no. All right, so this is an approximation when this is a small number. If that, I don't know if that's it's really 1/1 plus p6.
This number, the sticking probability tells you how many cycles in principle you can have.
Yes.
And that the overall number then cannot be larger than that. So
Correct. Yeah. So
I
this
cannot
is
take the tau fuse to be
yes.
zero
So
here, right?
that's right. So it really, this is the Taylor expansion of that, or the first term in the Taylor expansion. Yes. Yeah. So you can saturate. You saturate at the sticking time or whatever. Yes. Anyway, so that's another way for this to end up in a bad place.
Sorry.
Yeah.
So what relative concentrations have you in mind for deuterium and the tritium?
So the people play around with that, and then that's an open question. What the best one to use is, I think.
Can you get stuck where a dideuterium molecule picks up the hydrogen?
Yeah, there's yeah, exactly. And this is very density dependent and species dependent, temperature dependent. It depends on a whole bunch of things. But I don't know. I mean, this is some of my homework, I guess, is the point, unfortunately.
Do most muons end by decaying, not by sticking?
Yes, I think that's right. In this setup, if this number is small.
If it weren't for the sticking, this would be viable.
You
live long enough.
So the
for this to be
stick,
viable.
okay, sorry. So in the usual picture, what actually limits you is this the rate of forming these molecules. That's the but I'll talk about a situation where the sticking is what limits you, and where this probability actually with the formula that I wrote down is not quite right. Thanks to Maxime for pointing that out. Okay, so I'll just skip this because I don't really have any great ideas here, but this is what I should be thinking about, and that's how do you make this better? Okay, the basic zeroth order idea is, okay, well, we're going to be making a lot of muons. Well, according to yesterday in this country, and so maybe we can, this is some spin-off that we can think about, but okay. But it's kind of a mystery. One interesting thing from doing this kind of reading is stumbling upon interesting reports from, well, very, very Cold War type stuff, right? Because this is like involving nuclear stuff, and it's in the latter half of last century. And then you get, you stumble upon JSON reports, and these are all like super famous people. They get together and then they write a paper telling the US government like, oh, we should worry about this or not. And it's actually like a super fun thing to read.
Including Kunin, who thinks that global warming crisis is
Yeah, so they have a conflicts of interest, but I think he hadn't yet moved to BP. But he did eventually. But anyway, they have, they have all kinds of interesting words. They say, okay, the theoretical program is mixed. It's kind of funny. It's actually very readable. But an interesting phrase that you come upon is, okay, they talk about ways to improve, get that number up, right? And then they say these schemes often have an air of desperation about them, which is maybe fair, but it's kind of fun. Anyway, I encourage you to look this paper up or ask me for it. Okay. now let me segue into stuff that doesn't involve muons, but involves this same sort of physics. Okay. All right, we had to go from the electron to the muon. Let's go to something even heavier and negatively charged, and it can form bound states with nuclei. Okay, let's take the case of a STAU, and imagine that it lives a long time. And so this is possible in certain supergravity theories where the LSP is the gravitino, and because the decays into that thing have to go through gravity, then if the NLSP is the STAU, then it can live a long time, even up to a year. So, all right, now we're in business. We make a STAU, and then it lives for a year, just catalyzing these reactions. It's fantastic.
To live with very low reheating temperature or something.
Yeah, exactly. Yeah, but that's okay. Hopefully, there's but those are fun issues, and we get to solve a really deep issue that's affecting us right now. Here, the picture is a little bit different. You should really think about like this. The STAU is, its Compton wavelength is so small that basically it just, sits inside of the nucleus, and then you can now think of the, say, deuteron in this case with a STAU inside of it as being like a sort of a super heavy neutron. Okay, its electric charge has been neutralized, and so now there's no Coulomb barrier, and it can just go along and then bounce into a triton. And now here okay, so the 1 year, this is enormous. The rate limiting process is the sticking, and so now if you do some nuclear physics and then ask how often does the STAU end up sticking to the alpha, it's something like 0.1% of the time. Okay, and if that's the case, then that means that at most the STAU can catalyze about 1,000 of these reactions.
Well, you gotta pick it up or reaccelerate 3%.
Oh yeah, people talk about but then that changes the energy budget and stuff, because you have to put energy in.
12 G STAU.
Sorry, no, that means you get 12 GeV. So you make a STAU, and then you can extract from it 12 GeV of energy.
What's the mass of the STAU?
It's pretty independent of the mass, because it's here in the beginning and it's here at the end. It just is. It's literally catalyzing it.
It will. The mass of the STAU will determine how much money you will lose.
Yeah, exactly. Yeah. So the other side of this is how much energy do you need to pay to make one STAU, and it's probably less than 12 GeV. Or sorry,
How
more.
about to stop it though? You would just, right?
It kind of crawls along and it interacts. It's some minimally ionizing particle. And actually, that's a good question, because they made some of these things at Atlas recently. So there's all right. Anyway, I won't dwell on that. I'll mention another thing that this fusion process, catalyzed fusion, is useful for, and that's well, the catalyzation is useful in the sense that it means that you can get very good bounds on metastable things that live a long time, and long enough for light nuclei to form. So there's an interesting paper a long time ago now that Maxime wrote pointing this out. And the basic point is, well, in this case, for instance, because of weird nuclear physics again, you don't make a huge amount of lithium-6 in standard BBN. But if you have something that lives a long time and is negatively charged, then it can bind to the helium-4 that has to the progenitor of the lithium-6, and increase the rate of lithium-6 production by many orders of magnitude. And that increase by many orders of magnitude means that the limits on the existence of such things is quite strong. Furthermore, if there is a lithium problem, if there actually is too little lithium-7, which maybe there is, you can use this to destroy the mostly beryllium-7 that leads to lithium-7. So I think I'm done. All right, I'm not going to read everything here, but basically the point is, okay, I think it's worth thinking about what we can do with tons of muons and besides just a muon collider. Maybe, you know, we can even address like super deep problems or just problems for physics. And then here I've just shown a picture, you know, so even, you know, cool kids, this guy has a lot of tattoos, very cool. They have T-shirts that, you know, of albums that came out only 10 years after muon catalyzed fusion was first observed. So thanks a lot.
So I have a senior collaborator from Heidelberg, Evgeny Akhmedov, and
Oh,
so
yes, okay.
he claims that if there are doubly charged negative particles, then you don't have like the helium-4 is no longer a barrel because it's a neutral particle and it can you can reactivate that. And so his claim is that you know, like you can break even or even generate some energy. So this is you know, is in the top 5 among the most improbable schemes of getting rich.
How is excess with doubly charged?
Was it doubly charged? Oh, okay, yeah, so all right, thank God, yeah.
Yeah.
I know at some point historically, people got excited about the possibility of reionizing the muon from the sticking problem with,
Yeah.
you know, a big enough laser. In your literature research, where did that end?
I think then people are arguing about how you account for that, and then because it takes, I think the consensus that people have settled on is that it makes the problem worse because on the first off, it's not the rate limiting thing. It's just a you know, small 1% kind of perturbation as opposed to in the case of Staus where it is. And then also it changes the energy budget because now you have to also account for the laser energy that you put in. But people say, okay, well, once we figure out how to do that, then we can increase our efficiency quite a lot, make it much better. But that's it.
Maybe I'm just misremembering because I used to be quite interested in this when I was
Okay.
like a graduate student. And I was always under the impression that the sticking problem was the dominant problem for me.
Okay. Well, it's at least a problem that you can't imagine. So you know, people talk about the intrinsic sticking, I guess, and this is hard to, you know, that's some kind of lower barrier. This is nuclear physics, and you can't get around that. And then trying, you know, down the line, it could become the rate limiting step, and then you would have to start addressing that. So I guess if we do find Staus, then this would be, you know, the way to go, where you try, that is definitely the rate limiting step, and then addressing that would be a huge thing. But I guess it's, yeah, at least it's trying to reduce one of the or mitigate one of the like irreducible backgrounds in some sense, or you know, things on the wrong side of the energy budget.
So
Oh, no.
it's a fun topic. Thank you. So one of your energy budget changes if you think that you can dump some of the energy you use to accelerate and create the muons, or accelerate protons and create the muons,
Yeah.
into the target material itself.
Yes.
Somehow.
Yes. Yeah.
But that's
another consideration that I didn't talk about, but people do, when I put that like fancy eyeball looking thing, that people in the paper were saying, oh yeah, you get some of the energy back that way. Yes.
Yeah. And then the other thing, another thing, different topic, I guess, which people talk about is inducing, and I think I'll get this right, inducing decay of actinides using muons.
Okay. Yeah. So you could use this to breed those sorts of so I think people talk about like having, using this to breed various fissile material in your nuclear reactor, and that could actually be a useful thing to do, but I don't know too much about it.
It sort of cleans up, actinides have a half-life of 100.
Yeah, yeah.
Okay, thank you.
For the Stau scenario, I thought maybe I'm too young for Susie, but I thought the point was that
No one's
If
too
you
young. Like,
had-
no one's too young, right? We play all the hits. All the-
I thought the point was if you had like at least the styles that like you could look for at the LHC, for instance, are not excluded, you would have very long-lived and hard to stop particles. So I thought the point was they would just cross the Earth unimpeded, essentially, at those large masses, right?
Not the charge things you can stop.
But they're much heavier, right? So
Not that much. No, that's okay.
That was a fun talk. I would confess I know next to nothing on that topic. So just out of curiosity, if I take my magic toolbox, I set the sticking probability to 0.
Yeah,
What kind of energy budget you end up with then?
it's pretty similar to what I showed I think I probably dwelled too much on the sticking.
Oh, but sorry, but then you make you end up on the right side and you make energy out of it.
Yeah, so the problem is just the forming the molecules.
Yeah, so
That rate.
So I mean, if you don't get any sticking, the time it takes to form molecules at the muon decays, so you still end up with a positive energy budget. Even if sticking is 0, you need to find
Yeah,
a
you
way
would
to-
need to improve that. You need to make them 10 times faster,
Okay,
or maybe more than that.
so sticking is not really the.
In this case, as far as I know, but yeah, it seems to be something like 1%, and it's also something that you can dial by. Well, the sticking is itself also a little bit medium dependent in the sense that the alpha is moving along and it can get reionized by collisions. Which you can, you know, there are ways of trying to increase that, but there's some intrinsic probability, like if you were to do this in vacuum, that's the probability of the muon going with it, that you can't, that's hard to compete against. And then people talk about, yeah, using lasers to then accelerate and ionize the alphas afterwards. Yes.
Have a comment.
Okay.
So our mu based collider thing, we
Yes.
actually wasting mu minus. So we have some discussion of using that for muon catalyzed.
Ah, good. Okay, you should.
To energy back.
Okay.
Make the collider
Because the
cleaner.
yeah, I think yeah, that's probably the much more realistic thing is just mitigating, making things greener a bit.
Another thing is that I think there's a discussion that this process can be used for the cooling of mu minus.
Ah,
I
okay,
think JPEG has some study on that, so
okay,
that is another way.
interesting. Okay, thank you.
Okay, since we have run out of time, we can have more discussion in the coffee break. So we'll come back at around 3:45. Yeah. Okay. Thanks.
Boson changing?
So you're overlap.
We're sorry, the electric charge. It's just the charge that matters, right? But I think more.
But you know, I was under the impression that sticking.
Yeah.
So to get rid of the sticking, that it's.
okay. Okay, where?
Once you solve the problem, you can have reaction. Then it would be.
Oh, yeah, I mean, the super depends where you
Yes. So.
I didn't expect to find like. Yeah, that I know. It's a target study. Yes, but. Right, okay. Yeah. With CDS. And yeah, I think we might have mentioned it last night.
Delivery.
Yeah, that's right. That would be fun. Yeah, I mean, like, I don't see the process. Need a vector using right there.
But there's
Yeah.
a,
Yes.
there's a Walgreens, right?
So we just need to boost.
Yeah,
the
we
reactor.
both CVSM.
Let's do that. You want the whole like go through the atmosphere. Yes. Yeah. I know when.
Okay. All right, yeah.
Yeah, yeah.
Okay.
能够提前多久去机场？啊，Thanks, sir。
这边去机场要多少钱？也没有查那个。
这个时间我还真没怎么去过。其实这个时候坐那个那个 railway， 40分钟是肯定没有咖啡。但是对，
还得换一个
啊对，但同一站的就是
他们说好像那个 Uber 其实
啊，
有人跟我
对 Uber 是，
主要是可以先 check in，我是 wondering 是不是能坚持到
这肯定能去上早起，你这早着呢。
接下来还有2个 top 呢。
不只剩一个，就开了一个套
那个
开了一个就一个套，
我可以尽量坚持。
也是。
那在 Chicago 我的习惯都是提前3个小时不上。
你们芝加哥？
我芝加哥很
有飞机能问你吗？大不也？
Yeah, I'm heading up, so yeah. Good to see you again.
Yeah, keep in touch.
Yeah, definitely. So
Yeah, we have a common sort of interest. like
yeah,
I
absolutely. I was saying to Bernard, so if you know, for doing things like FFA simulations, like I speak to Yaroslav level all the time. We're working on an FFA lattice together, so you're on. And of course all the Muon things, but also the FFAs.
Sure, yes.
Yeah, we're building a magnet, so fingers crossed. Assuming no one cancels us, you know.
Also, please give my best regard to the Shinji.
Yeah,
I haven't seen him for a long, long time.
yeah, well, he's doing well. He's doing well.
Very.
Shares. Okay.
Okay.
Yes.
I don't care about this. I mean, I just don't, I'm sorry.
saw her face.
Yeah, she looked, yeah.
That's not gonna cut it.
For his wife.
It's for the.
Do you want to give it this?
Sorry. How are you? Yeah, that's why I said, oh, what did he do?
All right, thanks, I guess. You can stop.
Okay.
Yeah, very good, very nice.
No, but you're thinking that you might. It was not the main event.
No, no.
Okay, thanks. Oh crap, I just put.
Okay, we'll start our final session, and our final speaker is Patrick. He will talk about Dimuonium. Thanks.
Great, thank you. Thank you very much for the invitation to be here. It's been a very fun workshop so far. Let's see if I change that. Okay, so I'm going to tell you a little bit about some work I did recently with Sergo and Vladimir, both experimentalists at Fermilab. I'm a theorist at Fermilab. About a proposal to build a new type of collider. Well, actually, not a new type of collider to make a new type of thing.
Is that your picture, by the way, that you took?
Did I take the picture of Fermilab? No,
Reflected.
no, that's a corporate logo.
Oh,
Yeah. I'm contractually obligated to show that. No, somehow I've used the Fermilab slide template for one slide and then I gave up. Oops. Okay, and I didn't expect David to talk about what he talked about, so I thought I was going to be talking about something completely different, but this message. Okay, so let me talk a little bit about the bound states of QED. Some of them you know, some of them you don't know. So the hydrogen atom, of course, is a bound state of QED. Positronium, we talked a little bit about. Muonium is something that's been mentioned before in the workshop. I'm going to be talking about something that, depending on where you grew up, is either called dimuonium or true muonium. But it's a bound state of muon and anti-muon. This is a bound state of QED that's not been seen. Here are some other exotic bound states of QED. People have seen positronium molecules. So this is positronium bound to positronium. People have also seen pions bound to muons and things like that. Here are some other ones that we could go out and look for. So Taz bound to lighter leptons. But I'm going to be talking, like I said, about how to produce true muonium. Okay, so probably with this audience, I don't need to belabor the point, but a bound state of QED between a positive and negatively charged object, very simple system. It's the Bohr atom, and we can calculate the binding energy proportional to the reduced mass and times some fine structure constants. And the size of this bound state can also be calculated very straightforwardly. When I say straightforwardly, I'm hiding a lot of the details, right? It's ugly formulas behind the scenes, but basically, we know how the energy and size of the binding energy and the size of these bound states scale with the constituent masses. Okay. And of course, there's lots of interesting physics in spectrum. There's various types of splitting, fine splitting, hyperfine splitting, relativistic correction, Lamb shift, and so on that shift that break the degeneracy amongst the states. So just to remind you how things scale. So here we have the binding energy of good old hydrogen. The binding energy of positronium is, of course, half the size because the reduced mass is different. And then here's the binding energy of true muonium, dimuonium. And correspondingly, the size of the object is a lot smaller. And so if you want to understand what dimuonium or true muonium does, you can just open up your favorite quantum mechanics textbook and look at what positronium does. There's two types of states, right? 3s or at each level, there's two types of states, ortho and para states. The difference here is that for positronium, one of those states can decay to two photons, and the other one can only decay into 3 photons, and therefore the rate for that process is a lot smaller. And there's a sort of a hierarchy in the lifetimes of the two bound states. The difference for true muonium is that this one, which for positronium would decay into 3 photons, can actually just decay into E plus E minus finite states. So as a result, there isn't such a hierarchy in the lifetimes as there is in positronium. So these two states are roughly the same, have roughly the same lifetime because of this new open channel. Is there anything else I wanted to say here? No. Okay. So here is the spectrums of all the different bound states up to the n equals 3 level, along with their lifetimes and what they decay into. So the 1s state decays into 2 photons, as I said. The 3s state, which is the one I'll focus on for the rest of this talk, decays into E plus E minus. And then, of course, there's 2p, 2s states, and so on and so forth. And the 2p state, for instance, decays down to 1s state. Anyway, the thing to notice is these lifetimes, right, are short when compared to the lifetime of the muon. So as far as the muon, as far as the dimuonium is concerned, the muon is a stable particle. So these are very short compared to the lifetime of the muon. Okay. So the way one could go about trying to make this thing, as I said, it should exist, but it's never been seen. So there's a long storied history of proposals for how to make true muonium. Going way back to when, I don't have all the references here. Pion collisions, electron beams, photon beams, you've looked for them at RIC. More recently, there have been proposals from some people we know to look for them at the HPS. So the electron beam on going through a thin foil. You might expect that there are certain processes involving 1 and 3 photons that could make true muonium, and they calculated or estimated the rate, or rather the number of true muonium that you would get, depending on how much time you waited and how much current you put on the foil. You can also look for them in rare eta decays at LHCb. So there's a relatively rare eta decay into a photon and a band state that's got this branching ratio. So we're going to make a lot of etas at LHCb. So if we wait long enough, at the end of run 3, sort of 15 inverse femtobonds or so, you might be able to pick this out. You expect maybe 1,000 to 1,500 events, and either looking for them fully reconstructed or partially reconstructed, you could try to find this band state.
But they're being ripped apart by material, right?
For sure, yeah, they get ripped apart by material. They can't
make sure that they're not traversing the plates of velo.
That's right. That's right. They get ripped apart. I'll have a slide on that later. They get ripped apart very easily. That's right. But they took this into account in this case.
But you want to do spectroscopy at the end, no?
You may want to do spectroscopy at the end. That's right. Yep. That's harder to do. Yeah. Yes. Thank you for making my point. So here's an alternative way that was written down a while ago by Brodsky and Lebed, something they call the fool's intersection storage ring. So the idea here is, that's their name, not mine. So the idea here is you take two electron beams or electron-positron beam, and you cross them at some angle, so you don't collide the two beams head on anymore, you collide them at an angle, and you can make true muonium, but you make it boosted, so it moves away from the interaction region, right? It splits the difference between the two beams and gets moved away from where the beams are crossing into hopefully a quiet place where you can try to do spectroscopy or other things with it. Because of it's made off a virtual photon, you typically produce the 3s state, and whether it be 1, 3s, 2, 3s, so on and so forth. And the higher states, the rate for production drops as a cube of the principal quantum number. Just for simplicity, if you make the beam energy symmetric, as I said, the produced state gets boosted away from the crossing region, and the amount of energy you need in the beams scales with this angle, the crossing angle of the two beams, right? And,
Do you need the energy to be very precise?
that'll be an issue in just a second. Yes, you need the energy. They're very narrow, right? So the binding energy is small, as we saw. So just give me one slide and then repeat your question if I don't answer. And this boost, of course, the reason for doing it is because of the big background, right? So you can have, this thing is going to fall apart into E plus E minus, but just E plus E minus bar scattering gives a background that's the rate for that is a lot bigger. So, but it's prompt. So if you can move the decay point away from where the beams are crossing, you can cut down a lot of your background and hopefully distinguish the production of this state from the background. Okay, so the rate, as Leonta was saying, for the production of this band state, there's a very small Sommerfeld enhancement that's a fun calculation to carry out, but the bottom line is the rate scaled as alpha cubed, and then there's the price you pay of having the beam spread, the beam energy spread. That this is a very narrowly bound state, so you want the two beams to be right on resonance, and the binding energy is alpha squared m mu, and this is the amount of which the beam is spread. So that's a price you pay, but you only get to pick the piece of the beam that sits on it. Okay, so just to set the order of magnitude, that's the production cross section for picking some random value for the beam energy resolution, and then compare that to the background rate that I was talking about. You see, you have tens of thousands to 1 as the ratio of background to signal. So that sets the scale of the problem. Okay, so this is the theorist's idea, okay, of colliding two electron beams, and then sometime later, the experimentalists got involved and built a proposal or a diagram for a proposed set of beams that would collide electron beams at a big crossing angle to produce true muonium and along the intersection of beams. Okay, this is a proposal from people at Novosibirsk. And then Vladimir pointed out that we have lots of space at Fermilab, and we have lots of expertise in building beams, so we could try to do the same thing, the same configuration or something like it at Fermilab relatively easily and relatively cheaply. And so we got to chat. So the proposal was to use FAST, this area right here, and this is some pictures just to show that there's plenty of space at Fermilab. So the size of this thing is sort of tens of meters by tens of meters, and it fits very nicely, I'm told, in the space they have out there. Okay, so this is something that could be done, quote unquote, relatively easily. So what do you need? So if you imagine the beams cross at sort of 75 degrees, that angle that I showed earlier was 75 degrees. That translates into needing beam energy of about 408 MeV, so an electron beam and a positron beam at those energies. To get a high enough rate, you need a pretty luminous positron beam. And this leads to to all sorts of technical issues, all of which Vladimir tells me are surmountable. I'm not an expert in this area. The one thing that it does need, in addition to starting to build the thing, is it needs an extra cryo module because the fast beam can only go up to about 300 MeV, and you need to get up to about 408 MeV. But he said, this is the bottom line from him. You need a second cryo module, but there's plenty of space. So what's the big deal? Allowing you to get up to this energy. Okay, and of course you need positrons, so not just electrons. But he's come up with two different schemes whereby you can get a bright enough positron beam. And to a theorist like me, I don't see much difference between these two diagrams. It's all to do with when you accumulate and when you accelerate. But he claims it can be done. The one thing to note is getting these beamlines to join up requires fast kickers. But he's an expert on building these things and said they've already figured out how to do it for the ILC. And these things are no more fancy. So oh goodness. So the bottom line is that you can make such a collider relatively easily at Fermilab in this space that we have at the fast area. He claims it's perfectly suited. You can get bright enough beams allowing you to make about 500,000 dimuons a year. To be compared with those other numbers I showed you earlier, which were in the hundreds of thousands.
Your lines are no longer the lines, right? If they de-excite and so on, because it's boosted.
Oh, you mean they're no longer the lines are shifted?
Spectroscopy.
Yes, so let's take that into account. That's
they're
right.
no longer the lines, right? Because this thing is boosted, and depending where you emit your energy of the final state gamma.
Right, that's correct. Yeah. That's right. You're totally right.
You making it different.
Well, if you have a tracker, we'll get to building the detector in a second, but you can see where it decays from. You can see which way it's moving in and things. So you can presumably undo that. Right?
Yeah, so you first reconstruct the displaced electron positrons.
Yeah,
To say
right.
I produced the
Yes, you're this is great because I have a flight to catch, so we're going through the slide. You're going through the slides for me, so we're about to get there. But Jen's totally right. He's already seen the punchline. Okay. All right, so I think Maxime already brought this up. One has to be careful that you don't put too much material between the beams because once these things are made, they're very easy to dissociate. They're very weakly bound. As I said, it's typically made in the 3s state, right? Because it's made from a virtual photon. But if you were to, in transit, if you were to expose it to a strong enough B field or a laser or something, you might be able to pump it up into one of the other states and then watch for the de-excitations down to do spectroscopy. And then if you can get enough of these things and do the spectroscopy, you can measure all sorts of nice features of this system. And of course, this system is built out of 2 muons, so it's more sensitive to new physics. In particular, if there are new muonic forces, of course, that changes the binding of these 2 muons in some way, right? Changes the overlap of the wave function of the origin that we were being told about in the previous talk. So that can change both the production and the decay, but also if there's light muonic forces, it can also open up new decay channels that you can search for. So rather than this thing falling apart into E plus E minus, it might fall apart in some other way. And so there are exotic decay modes you could go after. And then, as you've already mentioned, there's spectroscopy that can be done if you can get it out of its dominant production mode. Of course, this idea doesn't exist in a vacuum, right? There are lots of other searches out there for muonic forces that place strong constraints. One interesting thing about this, about looking for these new decay modes, if they exist, is that going after them, you can distinguish the nature of the muonic force. So these curves are all showing the maximum possible branching ratio, depending on the particular spin of the new mediator. And these lines are all normalized to basically saturate G-2, right? So I dial up the couplings of these new states such that I don't get in violation with the G-2 results as they were at this time. So I didn't do this. This is some other people. And then I ask, how big would this branching ratio be for true muonium to decay this way? And you see that depending upon whether it's a scalar, pseudoscalar, axial vector, or vector, there's different predictions for the branching ratio. So you can distinguish different models. And these models all show up at in the same way at G-2. All right, so now,
So for what couplings is that? Did you fix the coupling or?
so I didn't do this, remember, I'm stealing this from somebody else, but you dial the coupling such that their effect on G-2
Oh, I see.
is saturates the rate there. And so you make delta mu as large as you can, and then you ask how big would the branching ratio be. Okay, running low on time. Okay, so Jen's question about the detector. So what type of detector do you want to build? So that depends on what question you want to answer. So first of all, it's never been observed before, so maybe that's the first step. You just want to see true muonium from the bar background. As you've already said, you'd like to do spectroscopy if possible. Searching for these exotic decay modes will be fun. And then anything else you can think of would be fun to do at the same time. Okay, so as I already said, I think I've already said all that. So in the interest of time, I'll keep going. Okay, so the first thing to do is you want to be able to see this displaced vertex, so that requires good tracking. Oh, it's not here. Where is the number? Oh, here it is. Yeah, so we're talking about millimeters of separation, so you need to have pretty good tracking. Maybe if you have very good tracking, these different band states, right, have different lifetimes, so they would travel different distances beyond the interaction point. So maybe you can, from the distribution of the displaced vertices, you can tell which mode you're making the true muonium in. So you need some amount of vertexing. So you need to use something like silicon here to be able to separate this from the backgrounds. You'd also like to measure things very nicely, right? To be sure that the more precise energy resolution, the more you can cut away the continuum background, which is the bar, like I said. So pile-up's not a problem. You don't have a high rate, so pixelization is not an issue. What you would like is high light yield, so you can get very good energy resolution. And so then there's a bunch of acronyms here that I'm not sufficiently qualified to explain. But the claim is these LISO crystals that we heard about this morning are very good at this, and that would be a reasonable way to build the calorimeter. They also give fairly good timing, which is nice. Okay, so here is a cartoon of what such a detector would look like. You have some vertexing there, so you can see the displaced vertex. So the silicon, then you have the calorimeter out here, and you have a few intermediate layers to allow you to match up hits here to hits in the silicon and get nice clean tracks. You don't need a magnetic field, and then Sergo thinks these numbers are sort of achievable. It's for acceptances and knocking you down from the 500,000 rate down to hundreds of thousands. So still a lot of events that you could hopefully do some precision physics with if you could do spectroscopy. So this is to see step 0, right? To see the displaced charge tracks. If you want to do the spectroscopy, you then have to ask, can you see these photons from the de-excitation, or can you measure the invariant mass of these electrons well enough to see which state they came from? Now that's probably challenging to measure, to identify the which state you're in just from the electronic tracks, because the energy differences are so small. But maybe it's possible to put something around that can measure the photons that come out, but we're not so sure about that. So the first step,
very challenging.
yes, very challenging. The first step is just to see it, right? It's never been seen before, so let's take baby steps before. Let's learn to walk before we run. Okay. Oh, and then Yuri made me put this in because this we went out for lunch the other day, and this was the. I'll leave it there without editorializing. Okay, let me conclude. So I think I've said all these things. So it's a band state of QED that's never been seen before. It gives a precision laboratory to test QED and also to possibly look for muonic associated new physics. This idea of using the Fool's intersecting storage ring can produce these true muonia states boosted. Typically make these ones. We have a proposal to do it at Fermilab that I'm told is not too expensive. What else? These are what the detector needs to look like, and This is the final goal. So I'll stop there and take questions.
So, if you were brave,
You don't know
could
me.
give us, you like, try to guess what the precision would be from the spectroscopy you could get
The precision on what?
on the energy levels? You do spectroscopy, somehow you solve all the problems that you flashed.
Are you asking from an experimental perspective or what you need to see the new physics?
Yeah, do you probe anything interesting is basically the.
I think it's hard at the moment. So I flashed by it. The sort of level at which the new physics shows up is here. Hundreds of megahertz. That's if you apply all existing bands, this is a sort of amount of change you could make. And that's tough, as McKeen was saying, from this alone.
Once, yeah, but once it's boosted, you don't have a line, right? You have a continuum.
Right. But the boost is right. That you know the beam. You control the beam very well. So the boost, right from the.
What?
I mean, you're saying the beam energy spread is probably too much. That's what you're worried about.
No, well, I meant is like if there is a gamma in the excitations, right? In a normal atom that's at rest, pretty well prescribed frequency, right?
Right.
This whole thing is boosted now.
But the boost, right, in principle.
Yeah, that's
Yeah, there's some Doppler broadening or whatever.
Yeah, there's some Doppler broadening. That's right.
Station.
Yeah, there's Doppler broadening.
I think we all kind of have the same skepticism that all you
yes,
get
I
at
think
the
so.
end of the day here is a very imprecise test of QED.
That's right. I think that's right.
It's hard to motivate unless there's like really some compelling reason to think you could find some new physics.
There's no compelling reason to think you find new physics. I think the strongest compelling reason is nobody's seen true Muonium, and we've been looking for it for 50 years.
Rejected a paper that said it abounded.
A long time ago.
I was an editor, yeah, he sent me a paper to review, I rejected it.
Oh, there you go.
Yeah.
Well, that could have ruined the whole talk. Yeah, exactly. Yeah.
Yeah, but this LHCb search for true Muonium, that sounds like it's an order one probability it will be.
Yeah, that's right.
successful.
That's right. Yeah, I think you're right. So if that works, that will be done and tested. If it doesn't work, you could do this.
There are claims that Bell 2 will do this.
Oh, is that right?
Yeah.
I don't know that one.
Yeah, I was gonna ask.
Well, Red Top just got.
Yeah, Red Top's not
Yeah.
not on show.
That's true.
This is not on show.
But this can actually get done, right? If
This could
somebody-
get done. That's right. Right. But
Something you don't need, I mean, you don't have a killer app. for it.
no, there's no killer app. That's right.
You got the money to do this.
I totally agree with Chris's.
And you said it first with this fortune cookie.
Yeah.
Even if actually find something on this, they wouldn't see the spectrum.
That's right. They also would
Yeah,
not see
yeah,
that.
they all just see the physics.
Right. That's so both of them. That's what we're both in the hunt to see true Muonium. That's
This one has a hope. If
How?
if his magical photon detection works. But how
McKeen doesn't believe in magic.
I mean, like if you see like if you produce lots and you see the distribution in the kind of lifetime of 3s, 2s, 1s, then maybe you can do some sort.
But that's more about
500,000 per year is pretty.
Yeah, 500,000 is a lot.
Yeah.
That's right. You can do a lot with 500,000.
How good the bargain is? How much?
I have no idea. You'll have to ask my co-authors.
But what's a unit?
I don't. I'm trying to remember what Vladimir told me.
Is it?
Tens of millions for the collider. Is that right? Is that possible? Chris will know. He knows these things.
Is this a ploy to get the positron source?
I'm sure it's a ploy to use fast for something fun. That's right.
Okay, great.
Oh, okay. I have one more slide. Since I'm the last speaker, I took the liberty of where's it gone? Putting together one more slide. on behalf of, oh crap.
I'll give you a talk again.
See how long it took me to realize that, that's terrible. Here we go, so I just wanted to thank the organizers for what I've really enjoyed this conference. So on behalf of all the participants, I just wanted to say thanks to all these people for putting on a great conference. So let's join me in thanking them.
And of course, we should also thank our staff that made everything super smooth. There wasn't any hiccup as far as I know at this meeting, so everything went smoothly, including the remote talks, which is like rarity. And all right, yes, I was saying that making it such a smooth meeting, and we had zero hiccups with anything. Everything went to the highest standards, and we all thank you.
When